of the function in this interval, then it is such a big interval because each interval is expected to have about infinitely many points. When it has infinitely many points, now I am coming for infinitely many points. In this interval, as I told you that there are infinitely many points, which is humanly not possible for us to define or verify the existence of this function at all the points or make any change to the function itself, the base function itself. Therefore, we say that it is an irremovable discontinuity. Well, dear children, we will be taking a few problems now on type 1 model. What exactly are we going to study in type 1? Type 1 or we are going to verify continuity of function f of x at some given points or point, whatever it is. This is exactly we are going to verify. You might as well think that what exactly we are going to do when to verify the continuity of the function. We will be applying all those three conditions which I have narrated. Condition number 1 is limit x tends to a f of x should exist. Condition number 2, f of x at x is equal to a should exist. Then further, the last and final condition is that limit x tends to a, f of x should be equal to f of x at x is equal to a. If these three conditions are verified for any function f of x that is given to us in the problem, it is as good as verifying the continuity of the function. So, let us take a few problems and then verify how a continuity to be verified as such. Well, dear students, as I told you, we will be now discussing type 1 problems. I have taken here 2 problems from type 1, wherein I would be discussing the continuity of the function at x is equal to 1. So, what I am going to do, first of all, I will take the points where I am supposed to verify the continuity. The graphical representation speaks very clearly that 1 is the point where I am supposed to verify the continuity. So, to the when x is greater than 1, this is very important point which you have to note down. When x is greater than 1, I mean on the right side of the number line to the point a 1, the function's definition is very interestingly x square plus 2, and to the left of 1 the function's definition is different, it is 2x plus 1. Then at x is equal to 1, I mean at this point the function's value itself, the function's definition is 3. Now, what exactly am I trying to explain you now? I am trying to explain you, when you try to discuss the continuity, you have to verify the limit. The very first rule or 1 is limit x tends to a, f of x should exist. This was my rule. So, in order to verify this, now what is limit? Limit of a function is always taken to the left limit and right limit as per the 11th class. So, when you say that left limit and right limit, if you take this interval 1 as 1 minus h and to 1 plus h, in this interval when x is approaching to 1 and x is approaching to 1 from right side, the function's nature, function's behavior itself different. So, now in this case I am supposed to find out the left limit and right limit because function is different on both sides of the 1. So, first LHL I will try to calculate limit x tends to 1 minus f of x, that is left limit. Limit x tends to 1 minus f of x is what according to the geographical picture, it is 2x plus 1. Then according to the rules that we have already learned in class 11th, I write this one as limit h tends to 0 and to 1 minus h plus 1, putting now h is equal to 0 in this, 2 plus 1 is 3. Now I will calculate RHL, right hand side limit. Limit x tends to 1 plus f of x is equal to limit x tends to 1 plus means x is approaching 1 from right side, that is the meaning. When it is approaching, the function's nature is different, it is x square plus 2. So when it is x square plus 2, what I need to do is that here according to the same what we have learned in class 11, I write it is h tends to 0 and 1 plus h whole square, x will be replaced by 1 plus h whole square because it is 1 plus, so it is 1 plus h. It is 1 minus, it is 1 minus h. So 1 plus h whole square plus 2. Now put directly h is equal to 0. What it is going to give become 1 plus h whole square, that is 1 plus 0 whole square is 1 plus 2 is equal to 3. Now it is very clear, therefore LHL is equal to RHL is equal to 3. Therefore when LHL and RHL exist, then we can say limit x tends to 1, f of x is equal to 3 and it exists. That means the rule number 1 I am supposed to verify for the continuity has been verified. So it is correct. Now I am going for the rule number 2. Rule number 2. Rule number 2 says that f of x value at x is equal to 1. That is f of x at x is equal to 1. That is f of x at x is equal to 1 already given as 3. So I will write f of x is equal to 3 as per given data. Then resulting the rule 3 establishing that the limit x tends to 1 f of x value and f of x value are absolutely equal. So limit x tends to 1 f of x is equal to f of x at x is equal to 1 is equal to 3. Therefore f of x is continuous at x is equal to 1. So my problem is completed for you. Now the thing is, when you have seen this problem, you have to understand one thing. When the function has different structures on the point, to the left of the point and to the right of the point, where you have to verify the continuity of the function, you have to go for LHL and RHL process. This is what you have to understand. Well, dear children, now I will be concentrating on the second problem. Interestingly, I will try to draw the graphical picture of this one. Here, the graphical picture is we are trying to discuss the continuity of the function at x is equal to 0. That means here is the 0 point. Now I create an interval 0 minus h and 0 plus h. Now let us see what the function to the on the either side of the 0 where you are verifying the continuity. Now x is not equal to 0. X is not equal to 0 means to the right of 0 to the left of 0, whatever values you take for x, all are not equal to 0. That means I write here at this position f of x is equal to 1 minus cos x upon x square. Here at this point also in this right side of the function point is also f of x is 1 minus cos x upon x square. So virtually what I am trying to prove for you is that here function is not changing on either side of the point where you are verifying the continuity. Therefore, you need not go for LHL and RHL, rather you can directly calculate limit x tends to 0 f of x, directly you can calculate. So how do you calculate? Limit x tends to 0 f of x is equal to 1 minus cos x upon x square. I would be writing this limit x tends to 0. I write this one as 2 sine square x by 2. Perhaps you must definitely know the rule that trigonometry rule 1 minus cos x is equal to 2 sine square x by 2. So that is what exactly I am trying to project it upon. Here 2 being a constant stands outside because we know the limit rule. Limit x tends to 0 sine square x by 2 upon x square. Here the rule that I have applied is limit x tends to a k into f of x is equal to k limit x tends to a f of x. So I got this one. Now I will try to do some more manipulations over the problem. It is sine x by 2 upon x whole square. Now this is going to be limit x tends to 0 sine x by 2 upon x by x whole square. I can put it because the rule says that limit x tends to a f of x to the power of n is equal to limit x tends to a f of x to whole to the power of n. The rule, this is the rule which we have already learned in class 11th. So now I have taken this. It seems to be a very familiar formula to us. What is that familiarity? We limit theta tends to 0, sin theta upon theta is equal to 1, where theta is measured in radians. Now the thing is, exactly I am trying to locate this formula here. If I consider x by 2 as theta, here in the denominator I have x only. So I am bound to make it as x by 2. How would I be making it? You can see here now. Limit x tends to 0, sin x by 2, and I do it x by 2 here. That means I have multiplied the denominator by x by 2. I would be multiplying rather the numerator also with 1 by 2, and a whole square which was prevailing previously has now come into the picture. So what I would be trying, this is also being a constant, again applying this rule, I will take this one out, then it becomes, I think 2 was already there outside, so I would be taking that also. Now what happens, 2 into the 1 by 2 coming with the square as 1 by 4, limit x tends to 0, sin x by 2 upon sin x by 2 whole square will remain as it is. This is exactly replication of this formula, that is limit theta tends to 0, sin theta by theta is equal to 1. Therefore, you get 1 by 2 into 1 square is equal to 1 by 2. This is the value. Therefore, limit x tends to 0, f of x is equal to 1 by 2. Now, as per the problem, the rule 2 says f of x at x is equal to 0. According to the problem, what is f of x at x is equal to 0? It is 1. It is being 1, what I can say, it is 1. But now you see, do you think the value which you have obtained in the R1 and the value obtained in R2 are same? No, they are not. That means the limit x tends to 0, f of x is not equal to f of x at x is equal to 0, which implies that f of x is discontinuous at x is equal to 0. But what is this kind of discontinuity called? It is removable discontinuity, because rule 2 does not exist. It is modifiable. If you modify, then this function is going to be a continuous function. You may think that, sir, how to modify? Though it is irrelevant as far as the problem is concerned, I would be trying to give you a bit more what exactly you have to understand. Here, if I change the function's definition as f of x is equal to 1 minus cos x upon x square, where x is not equal to 0 and it is half in x is equal to 0. What is the difference between this function and this function? I have just replaced the 1 by the half. That means, had it been instead of 1 half, then perhaps I could have claimed that the function is absolutely continuous at x is equal to 0. Thank you. Well, dear children, we have already learned 2 problems from type 1. Now we shall be concentrating on 2 problems of type 2. What exactly we are going to learn in type 2? This is a problem where the function is already declared to be continuous and we are trying to find out a value which is given as an arbitrary constant. So in this problem we are going to find out a comma b, and in this problem we are going to find out k, subject to the condition f of x is continuous. Now that means the function is already continuous. Now let us begin with that. F of x is already continuous. Please remember, at x is equal to 1. What does it mean? Limit x tends to a, f of x is equal to f of x at x is equal to a is the clause. That means this is already satisfied. Both are equal. Now to begin with, now let me see first of all the graphical picture of this function. Now the graphical picture where 1 is the point where it is already continuous. To the left of 1, what is f of x? It is x square minus 2x minus 3 upon x plus 1, and to the right as well, f of x is equal to x square minus 2x minus 3 upon x plus 1. That means the point where the function said to have been declared continuous, both sides of the, either side of the point 1, the function is the same. So now in that case, you don't have to go for one-sided limit process. When we go for one-sided limit process, when we get both sides the functions are different. Now here in this case they are unique. So now I shall begin with limit x tends to a ke badle mein that we will be taking 1. that is x square minus 2x minus 3 upon x plus 1. Let us go for a factorization of this. Limit x tends to 1, what it is going to be approximately, I think x square minus 3x plus x minus 3 upon x plus 1. I hope you are able to understand middle term splitting. Limit x tends to 1, x minus 3 and x plus 1 and upon x plus 1. Here this is getting cancelled. These two are cancelled. You get x is equal to 1 substitution in the remaining factor. It is going to give you the value of minus 2. And if you take f of x at x is equal to 1, what it is at x is equal to 1, you look at here at x is equal to 1, the function f of x value is k. That means it is k. As per this rule, function is already continuous. That means this is already whole good. That means therefore, limit x tends to 1 f of x shall be equal to f of x at x is equal to 1, which means k is equal to minus 2. Therefore, k is equal to minus 2 is the value for us. Well, dear children, now I have taken this problem here quite unlikely of the previous one. Here you have to find out two values a and b. So, how am I going to find out? First, let me see what exactly the data given to us. Now, in the data given, he said he declared f of x is continuous function at x is equal to 1. Now, let us see the point where the function is continuous. What is the function's nature? See, to the left of 1, where x is, this is I think x is less than 1, I am sorry, it is x less than 1. So, when x is less than 1, in left side, it is 5ax minus 2b. To the right of this is f of x is equal to 3ax plus b. Now, at this particular function value, f of x is equal to 11. So, now what exactly I am trying to speak to you, when the function is different, having different structure on either side of the point where it was declared continuous, you have to proceed with one-sided limit process. Why? Because function's nature in the left side and right side are different. So, now the rule speaks, whenever the function is continuous, what is the rule? Limit x tends to a f of x should be equal to f of x at x is equal to a. Now, as far as this particular condition limiting value is concerned, limiting value of the function is directly calculated when